So what is cover? Perhaps the simplest definition, this is one I've modified from Steve Hill, is that it's earth material overlying an exploration target, typically sediments or overlying crystalline basement. Okay, the regolith, that term regolith, includes a lot of the cover but not all of it. So regolith perhaps is most easily described as everything between fresh rock, unweathered rock and fresh air. It includes in situ material, such as shown here, this open cut mine, a highly weathered in situ regolith profile developed here, and also transported materials like aeolian sediments, alluvial sediments, colluvial sediments and so on. These materials can be unconsolidated or semi-consolidated, or they could be quite hard where they've been later cemented by silica and other elements. So cover, not everything, I'll just go back a sec, not everything in the regolith includes the cover. So unweathered Mesozoic rocks, you probably wouldn't include that as regolith, but you'd certainly include that if you're searching for base metals. So the Mesozoic material would be cover. But it covers a large part of it. The reason it's important that we look at this is that, like a good bottle of Shiraz, Australian landscapes are old, flat and red. We have less than 20% exposed rock at surface. We live and exist in a highly weathered landscape. Rocks at the surface are old, and perhaps more importantly, they've been exposed at the surface for considerable periods of time. We've got situations where in the Northern Territory we've got Cambrian alluvial terraces which were exposed at the present time. These are some 500 million years old. So it's a very stable crust. The other thing that preserves a lot of the weathered materials is it's very low in relief. It's one of the flattest and driest continents on Earth. And if you get some statistics out of the shuttle DEM, the 30-metre DEM over Australia, on average it's 1.3 degrees of slope over the whole of the continent. So it's very flat. So we're in a very atypical part of the landscape. Most of Australia looks like this. And the fact that we've got semi-arid climate and very low process rates due to the flatness, a lot of the material is preserved, weathered material preserved. And this is reflected, of course, in the surface geology map. We've seen this before. A lot of the yellow wash in here is cover materials, and even the greens are Mesozoic sediments. And we've got islands of basement material poking out through that. And I think a lot of people have seen this slide many, many times, but it has a big impact. These are the major mineral deposits, and of course they overlie areas of outcrop. When I look at this, there are two things that stand out. One is that from an optimistic perspective, we potentially can find a lot more deposits in areas of cover. The other thing it really emphasises to me is that our geological framework is largely based on surface mapping. We've done a lot of work with the use of geophysics, particularly airborne EM, in local areas to really get an idea of the structural complexity of the cover material and image basement material depth. But on a national level, we don't have a national map which describes the thickness or the nature of that cover material. And that's what we're trying to address in this talk. I think a lot of people saw that regolith mapping back in the early 90s, and this is when I joined BMR, or GA at that time, was going to solve this problem. We saw the cover as being a regolith issue, and regolith landform mapping was going to really provide insight into the nature and character of that cover material. The concept of a regolith and landform map, the reason we associate the two is there is a close spatial and genetic association between landforms, as you'd expect, and the regolith materials. Okay, and a lot of this mapping initially is based on air photo interp, and later we augmented it with the interpretation of radiometrics and DEMs and various other things. But unfortunately, it was surface-based mapping. So I'll give you an idea. If you're in this sort of landscape and you're going to produce a regolith landform map of this landscape, you would basically split it up into the hilly bits, which are your erosional saprolite parts of the landscape, and you'd delineate these colluvial slopes, and probably at the break of slope, you'd delineate these floodplain sediments. And that's pretty much as far as we got in terms of splitting these sort of landscapes up. We wouldn't be spatially explicit in terms of the depth of this material out here, but we'd separate packages of landforms and regolith in a regolith landform map. Now, of course, if you've got this situation, landforms is completely wasted time. This is one landform type. Using landforms as a surrogate to map regolith is just not going to work. It's just ineffective because essentially it's a surface mapping approach. Now, To really demonstrate this, this is some work I did with Mike Craig back in 2000. We were asked by a mining company, this is some work in South Australia in the Gawler region, to produce a regolith landform map because the company at the time was struggling to interpret their calcrete gold geochemistry. So we came in and did this map. It's a much bigger area than what I'm showing. And we separated out, as you would do in a regolith map, the colluvial material here, calcareous material because that was a very important geochemical sampling media, and then we had to go picking out the residual bits, the in situ bits, and we found elsewhere in the map sheet that ferruginous lags were sitting on top of basement rocks, and so we extrapolated that through the area. We were pretty happy. We did a lot of Landsat interp, wasn't just based on landforms, and we did the map very quickly. Unfortunately, a year later they flew airborne geophysics, airborne EM, and somewhat embarrassingly we miss a major architectural element. These are big paleo channel systems running through the area. We didn't map these out at all. This is imaging into the subsurface now. These paleo channels are highly conductive, and you can see the dendritic patterns of these channels. So first order subdivision of what's transported and what's in situ is totally missed by the regolith approach. I'm still going over the embarrassment, so I'll just go through there. Maybe this is the driver for the PhD 10 years later. If we have a look at more of our sort of regional mapping, this is a surface geology map. There's Mount Isa Inlier in here, Mount Isa somewhere in there, there it is there. I'm comparing now the surface geology mapping to a regolith landform map, and I've just clicked on a polygon, transported unit, and the description is alluvial sediments, gravel, sand, silt, clay. If we click on the same unit in the regolith map, we get this similar, very vague description of what the materials are. No inference on how deep they are, where the gravel is it evenly mixed, are the lenses of clay, and this is the sort of thing we need to address. And this brings me back then to this gap in our knowledge, essentially, brings us back to the Uncover initiative. And really this is about substantially increasing our success rate of exploring for minerals in greenfields exploration environments beneath regolith and sedimentary basins that concealed undiscovered mineral deposits. And a lot of what I'm talking to, there are 6 pillars of this research. I'm focusing on the characterising the cover. Now I argue that we need to be much more quantitative in our predictions. It's not good enough to say it consists of sand, silt and clay. We need to know much more. So if you break that down, we need to know if it's in situ transported, the provenance of the material, more detailed maps and descriptions of its geochemistry, its weathering intensity, and fundamentally its depth. This has a huge impact in terms of exploring and developing exploration strategies. We don't know that nationally, and of course its age. This information can feed into a much greater understanding of geochemical dispersion and development of more effective geochemical exploration techniques. But of course it's not just the depth, we want to know what that material is, that volume of material. Particularly, you could probably add to this list, we want to know the texture, permeability, porosity, conductivity, density, lithology. They're all important. These sort of things help us interpret our geophysics. Separating anomalies in the basement, we need to understand how that cover influences those magnetic responses. But it's more than that. This feeds into groundwater. If we're trying to map water storage and flow systems, we need to know about these properties because they control a lot of water flow in the landscape. And incidentally, this information also feeds into hydrogeochemical modelling. And this then builds into agricultural landscapes. I mean, a lot of this work can feed into this area. It's not a core business of GA, but we actually contribute enormous amounts of geospatial data which really help people that work in this space. So our airborne radiometrics underpins a lot of very detailed soil mapping which support the farming sector. There's a perception now that it's not just about the top metre or two of soil. We need to look at the complete regolith, the water storage capacity, the fact that deeper regolith has a strong influence on the fertility of these landscapes. And I think there's a lot of work here in the next couple of years which will come out of analysis of the data cube, particularly temporal change, looking at deep drainage and so on, that can inform on these types of landscapes. So there are lots of reasons why we need to understand these materials better. If we're going to map the cover, we need to map gradational boundaries, sharp contacts, because this is what you see in the real world, both horizontally and vertically. I would argue we need predictions at an appropriate scale. I'll show you later a national prediction of regolith thickness at 90 metres. That's the sort of scale or resolution we need to work at. It's also hard. If we've got drill hole information here and we're trying to map this interface of the regolith between these points, it's difficult to do. It hasn't been done before. I mean, we wouldn't be here talking about it. It's tricky. We have to have a go, but we have to demonstrate our uncertainties. That's important. So let's just think through. If we are going to predict the thickness of cover, we could draw information from a series of data sets. We've got airborne radiometrics. It maps the surface chemistry down to about 30 centimetres and infer depths down to maybe 3 metres, perhaps deeper, based on some relationships between weather intensity and depth. Terrain attributes, very useful in areas of shallow cover. Topography has a strong control over materials in those sort of settings. As you get deeper into a basin, though, the topographic control is lost. Okay, and we're relying on other surrogates. Gravity, density contrast between cover and basement. Sediment's usually less dense than the basement rocks, very useful. However, we've got a resolution issue. Magnetics, probably the most important data set we have for a national prediction of cover. It's useful if there's a magnetic contrast between the cover and the basement. And then finally, airborne EM, again, very useful, but it's patchy coverage. And it relies on, we've got a conductivity contrast between those basement, the basement and the cover. And the other thing that's really important is if we're going to do any of this work, we have to build on what's been done previously. So we have to integrate geological mapping and regolith mapping and also drilling, site information where we have a lot more control. So the message here is it's not one silver bullet, it's about a complete fusion of data and integration. And one way of doing this is using what's broadly termed machine learning, where we're using tree models for classification and regression. And a lot of what I'm going to talk to you about has been used or developed in the last 10, 20 years in digital soil mapping, and there's a nice review paper, although it's getting a bit old, by Alex McBratney. But also I want to bring in this concept of environmental correlation. Neil McKenzie and Mike Austin use this term for predicting soil properties based on environmental covariates that reflect the factors controlling soil formation. It's solving this equation, which I'll come to later. Basically, if you build a set of covariates which are proxies, the thing that you, for the actual control, those proxies control the formation of those things that you want to map or model, you could use those in your modelling as prediction. Elizabeth Bury did some excellent work demonstrating how data mining can be used to map soil properties. And within GA, there's been some excellent work, and I've just picked out one here. Jin Lee has done some work using random forest machine learning for mapping seabed substrate. What I'll talk to you about is this algorithm called QBIS data mining, and it uses regression trees. And I'll explain to you what that all means in a minute. But just coming back to this predictive data sets, these covariates. So the idea here is you want to build and construct a lot of covariate or predictive data sets which cover the factors controlling the formation or distribution of the property you're trying to predict. Okay? So for digital soil mapping, they try and solve this equation, that a soil attribute is going to reflect a combination or be a function of climate characteristics, organisms, vegetation, topography, parent material and time. Okay? And this goes back to the early work of Jennings in 1941. Soil is the upper part of the regolith. We can use this overarching framework to do our predictions. Our depths are much deeper, our properties are different, and we have a richness of information which inform on particularly the parent material and the lithologies, magnetics, gravity and airborne EM. So broadly we can use a similar sort of approach, albeit for a very different application. So now I'm talking about environmental correlation. This is about using predictive data sets to actually predict the thing that you want to map spatially. And there are several components to this. I'll just run through this quickly because I'll explain these in more detail later. You have your site observation, which might be drilling or some geochemical data. You build your covariate suite of data. You intersect the two and you generate a matrix table. From that you start your machine learning algorithm. In this case we're using QBIS. It's not a black box, it's actually quite transparent. You can see how it works, and there's a very high degree of knowledge discovery component in it, and I'll illustrate this in the talk. But you don't run the model once, you run it many, many times, and I'll explain why. And then from that, so this is actually try and find correlations between those two things. From that you generate a predictive model and you generate model uncertainties. So let's go through that one by one. So your site measurements or observations, essentially that's your target variable. That's the property you want to predict. Okay? If you want to be quantitative, you need quantitative site data to train the model. And some examples of this are multi-element geochemistry, geochemical survey data, and drill hole depths, okay, from drilling, or inferred from magnetics or seismic depth estimates. So, and there's some examples I'll show in the talk. The other very important component of it is you've got to build this covariate data suite of information, if you like. It's sort of similar in many ways to the data cube. You want to build all these layers of information which will inform on the property you want to predict. And you don't just throw everything in. You're parsimonious. You put in what you think is going to be important. And so you build this data set. It's taken quite a long time to do this. Terrain attributes of geophysics, satellite remote sensing, so the MODIS and ASTER, and eventually the Landsat data will go in. We've got climate attributes. You'd think climate perhaps wouldn't be important, but if you're predicting things like carbonate distribution, it is very important. Existing data sets, regolith soils and geology, and derivatives, okay, from these data sets are also very important. So the success of environmental correlation really depends on strong relationships between your target variable and the environmental predictive data sets. So you take quite a bit of time compiling this data. And this is just one example which I find quite fascinating. Time series MODIS. There's a great temporal richness of MODIS data, and if you look at just purely greenness, okay, greenness variation through time, which is what this is showing. So if you drill down through 1 pixel, this is work by Leo, you can get these fluctuations in greenness through time over about a 10-year, from 2000 to 2011 time period. And why would that be important? Well, if you look at coefficients derived from this and display them as a 3-band image and compare it to the radiometrics, although the colours are different, the patterns are very, very similar. One is measuring surface geochemistry and one is measuring variations in greenness, patterns in greenness through time. And yet the actual patterns here are very, very similar. And I think what we're seeing here is that your first order of control is going to be climate and vegetation type in terms of controlling greenness. But then it's the water storage in the soil, which has a big bearing on the rate of greenness decline through time. And you can sort of pick out these rates of decline, okay, and they relate to water retention in the soil, which relates to porosity and permeability, which then has a relationship to geochemistry. And I think we're seeing in these water stress environments a very close tie-in between vegetation patterns and surface property of the regolith. So we can use MODIS as a predictor of surface geochemistry, and I'll show that in a minute. The other thing, the Landsat data cube, is that because you've got temporal richness, we can go through, that's what we're working on at the moment, and pull out pixels which have a very low green response. And so what we want to do is really enhance areas of bare cover, because that's a soil signature that we want to extract. And some preliminary work with Adam's group is that we're demonstrating that we can also remove some of these fire scars shown through here. They disappear as you pull through or go through, sort through the data and extract pixels which have low green response. So this is going to be a very important covariate in our predictive modelling. The other thing you can do, you could put in these outcrop polygons. Okay, this is one of your covariate data sets. But it's probably more useful if we put in a map that shows distance from outcrop. Okay, so greater distance from outcrop in red. And you can see how this potentially could be very useful for mapping cover, Cenozoic cover, and it is, in fact. So I've discussed the covariates and the observations, now the modelling approach. Okay, how does that work? Okay, the QBIS model structure looks like this. It's a coupled system where we've got a decision-based classification tree, and at the end of those branches of the tree we have these multiple linear regression models. Okay. The nice thing about QBIS, it can handle continuous as well as categorical data, so you can put in your geology and your radiometrics in there. And the rules you can look at. You can interrogate these rules and look at how it's mapping out these relationships, and that's part of the knowledge discovery part of it. It also, because of this coupling, it can describe data which is non-linear. So there's many advantages to it. Now the important part here is that what we're not doing, we're not interpolating between our points. So if these are drill hole locations with a regolith depth, this is not interpolation. It's actually a model. What we're doing, we're modelling at each of the pixel locations within our predictive grid based on the relationships between the covariate datasets and our target attribute. Okay, so it's not interpolation or kriging. Okay, now the way we implement, we don't run the model once. What we do, this concept of bootstrapping, is that we take out random sets of data. Okay, well, first of all, we take out a out-of-sample validation set. So this is used to assess the performance of the model. So that's removed first. It's usually 10 or 15% of the data. And then what we do, we randomly generate subsets of the data and run a model. And each time, for each cell in our output grid, we generate a prediction. And we do that 100 times, and I'll explain why. And so we build up variance around that prediction. We use a median value as our predicted surface, but then the spread of that data, of those model outputs, we can use that to estimate the degree of certainty. So the broader the spread, the more random the predictions are for any given area, and the higher uncertainty. And typically what we do the difference between the 5th and the 95th quantiles and described as a 90th percent confidence interval. So it means that 90% of the time, the value that we see, that we map, appears in that range. So if we ran the model once, we wouldn't have, using this method, we wouldn't have any uncertainties. Okay, we're doing it once. If we ran it a second time, we'd start to build up some variance and some uncertainty, and we keep on running the model again and again, and what we find is that, and it might be hard to see this is the number of bootstrap iterations, so this is 100 here, and this is a variance within the prediction. We get a plateau at around about 100, which means we're not getting any more variation in the model. Okay, so perfect model would be down here, we just run it once, we wouldn't know about variance. Around about 100, that sort of levels off. So we tend to run the models at around about 100 times. Model evaluation, you can do this in many ways. I'm just going to describe two. We use an R-squared correlation of the out-of-sample. So we intersect that out-of-sample subset back to our model and look at the relationship, the R-squared relationship. And the other thing I've just touched on is that we're looking at model uncertainty. Essentially, we're looking at the 90th confidence interval based on the difference between the 5th and the 95th quantiles. Okay, we can also express that as a ratio to the median. Right, let's look at an example of geochem modelling. Okay, this is an area in Western Australia. It's a Samuel map sheet. So we're in Archean terrains. We have these greenstone belts running up through here, which you can just see. These magenta colours are mafic rocks. There's another one running up through here. But the area is very poorly exposed. So a lot of what we have here is regolith. We've got aeolian materials and sheet flood fans and these sort of yellow colours through here. And we've got some lacustron and lake sediments down through here. Okay. Let's take some surface geochemistry from the Geological Survey of Western Australia. This is some data from Paul Morris. We have a very nice data set. I mean, this is where they've gone out and sampled multi-element geochemistry of surface. And here I'm showing you the distribution of chromium going from about 17 ppm up to about 2600 ppm. And you can begin to see some patterns. And as you know, the chrome is highly correlated to the mafic rocks, particularly ultramafics, and we're beginning to see some trends through here. If we Krieg that data, this is just gridding between those points using a Krieging method. We get a nice sort of blobs around those high areas, okay? And it's, you know, it's some pattern there, but it's a bit fuzzy. Now, running the QBIS data mining approach, okay, we've separated our out of sample. We'll remove that because we'll look at that later. We then generate with this bootstrap a training set and a validation set. So the training set's in yellow, validation in green, and we do this many times, 100 times, and each time we're generating a prediction at the resolution of the covariate data sets, which in this case is 90 metres. We also log transform the data because it's heavily skewed, and that gave a better result. So when we do that, we generate this. So this is a prediction of chrome now, surface prediction using environmental correlation and the QBIS algorithm. The out-of-sample correlation, this is where that out-of-sample subset, we intersect that back, and we get a very strong correlation, 0.74, between the model response and the actual value And the interesting thing about this is that it adds much higher fidelity in terms of the distribution of chrome in that landscape. See if you can compare the two. Let's explore that in a bit more detail. The other thing you can look at is you can list the important covariates in that prediction. And up the top here we've got this MODIS, which I alluded to before. Radiometrics, gravity are important. And I'll just show you a couple of the key covariates in that prediction. We've got gravity. Perhaps not surprising, these mafic rocks here are more dense, so you get higher densities through here and less dense sediments or granites in between them. So you can see how it's broadly using gravity to partition out those high chromium areas. The MODIS satellite adds more definition, and so on as you trickle through all those covariates. They all contribute to that prediction. In this environment, we've got a very close connection between the covariates and our chrome prediction. So uncertainties are very, very low, which means the distribution of these things are very tight and narrow. Okay, so a lot of the high uncertainties relate to very low concentrations of chrome. These are little granitic breakaways through here. We also have an anomalous area up there, and interestingly, when you look at that, that corresponds to the Mount Keith mine. So that's probably not surprising, because the disturbance of the mine activities here would destroy any environmental sort of pattern that the model would have found elsewhere. And so that's why you've got high uncertainties in that particular area. We can do the same for iron oxides. Okay? So this is at a resolution of 90 metres, and picking out these ferruginous materials. And you'd expect those to be highly correlated with the chrome, and they are. So this is outcropping mafic and ultramafic rocks, these magenta colours. This is high chrome values in red, and you can see a high correspondence. But a lot of this elevated chrome is related to the regolith cover, particularly the ferruginous material. And this shows an example here. Some work by Ravi and Ann. These are your ironstone gravels, your sort of ferruginous upper part of the weathered profile. And this through here is your chrome. And you can see that it's scavenged by the iron oxides and probably sits there as chromite, which is fairly immobile. Let's look at it as a 3D perspective. There's a lot of detail here. So we've got, because chrome's not particularly mobile, you get these areas concentrated in these topographic highs through here, very little dispersion into the sheet flood fan system. You get slight elevated chrome in these highly weathered granites, and very low values around where you've got freshly exposed granite through there. So there's a lot of information about the distribution of chrome. Now we can run lots of models for many different elements. Interestingly, if we do it for sodium, it's a totally different picture. Sodium is related to the granites, the feldspars in the granites, but also accumulates in these sediments. Halites and things like that in the channels, the clusterine channels. Okay, so the patterns are much more complicated. These are some of these big bluff-forming breakaways that you get up through here. We could do the same for uranium. Now, interesting, when I ran this model, I took out uranium, the geophysical uranium as a covariate, so this is without that. That's just highlighting the main channel systems. And then we can model uranium, okay? And there's Uliri there through here. High uranium associated with the granite catchments, and again high in these paleochannel sediments. Now, because we're establishing predictions or relationships between our target variable and these environmental data sets, we can extrapolate into areas, as long as, in this case, the geology is similar and the landform history is broadly similar, and that's probably the case for an area that's relatively small. So here I'm just going to create a model based on half the data and compare it to using all the data points. And they're almost identical. Okay, so they're identical because the relationships are robust. And it's not finding patterns in here which are any different to the ones in here in terms of the connection between the concentration of this particular element and those covariates. Okay. The other thing we can do is that we can look at the sensitivity of this. If we reduce the density of samples, so we take out subsets of the data and generate a model and compare it back to our out-of-sample subset, and compare, say, the chrome with Krieg data, okay, where we've got a model where we've removed we've actually retained 70% of the data, so in this case it's about 700 samples. We get quite a strong prediction. This is the R-squared prediction. The higher you go, the more stronger the correlation, okay? That's what you want. So initially, if we're using about 700 points, we get quite strong predictive power, and this drops off as we reduce the number of sample points, okay? So we do get a drop in the Cubist modelling, but we get a substantial drop, particularly when we drop down to about 10% of the samples using kriging. So this data works well without high sample intensities, as long as those sample sites represent the variations you see in your covariate datasets. Let's have a look at nickel. This is now concentration of nickel going from about 3 ppm up to about 500. It's fairly low in this area. And there's some nickel deposits, which I've overlain. It's got a nice correlation. But we can upscale. You know, we can use more data. In this case, we've got 12,000 geochem sites, and we're modelling the distribution of nickel. That's a Samuel map sheet, and this is a much bigger area. And I've made this map semi-transparent to the underlying magnetic intensity map. And you can see these sort of greenstone belts through here, and a quite strong correlation between the nickel deposits and the predicted nickel distribution from modelling. So we can use that same sort of methodology to map thickness of cover. So let's have a look at that in terms of firstly mapping the depth of regolith as a national product, and then later the thickness of Cainozoic sediment in the Murray Basin. This work really is, and a lot of people involved in this, it's what we're doing is we're building a point database of depths from drilling, but also estimates from geophysics, from seismic reflection, from magnetic inversions, passive seismic. They all provide information on the depth of cover, and what we're doing is developing a new database to store and house this information, and it's called Estimates of Geological and Geophysical Surfaces, EGS. Okay, and from that data set, we want to generate surfaces, and that's sort of the work I've been involved in. And we're going to start off with producing a national map of Cenozoic thickness, okay. We've also had a go at producing a map of regolith or weathering depth, okay, and we see this as an overprint over these materials, all right. So let's look at this first. Okay, this is a block model showing regolith, and what we're aiming to do is actually map the surface down to about this interval. Corresponds to the sort of saprock or lower saprolite boundaries, where you probably recognise a lithological material in drill hole. So we're trying to predict this interval down here. And where there's some drill holes, and where we're doing this, we're using the National Groundwater Information System database, because it's a national database, and there's been a lot of work in cleaning the data and collating it from all the states. And when you look at that, you get quite excited. You think, okay, we've got almost 1 million drill holes here. Unfortunately, there's only about 357,000 with lithology descriptions, but that's a lot of data. And then you look at it a bit more closely and you realise, oh my God, it's quite a mess. The descriptions are very poor, they're inconsistent. We've got spatial inaccuracies prior to GPS, 1990. You know, if you had 6 people interpreting the boundary from these drill spoils, you'd probably get 10 different answers. It's difficult to work with. What we've done is develop some ways of extracting what we think is a useful interval from this data using automatic text matching. And we've also done quite a bit of work in trying to filter the data, take out things which are odd in terms of understanding what we'd expect from our weathering and landscape history knowledge using other more reliable data sets. But I won't talk too much about this. Let's have a look at the automatic lithological matching sort of routine. So what we did, we actually built up a dictionary of lithology words, okay, and then we drilled down through each individual hole, 357,000 of them, and tried to find where that word matched a description in the drill log. And it does something like this. This is a nice clean data set. It never looks as good as this. And we've got granite picked up here. So this routine will automatically sift through recognise that's a bedrock term and pop out a depth of 30 metres. Unfortunately, we also have to account for lots of spelling, lots of derivations. So these are different spellings for granodiorite, and it gets more and more obscure the deeper you go. This took several weeks of work sorting this out. Spelling of siltstone, and I was going to put up various spellings of schist, but I'll let you use your imagination on that one. But it's a way of dealing with a huge amount of data. So we got a little bit excited, and we'll now tag these depths. Okay, so what we think we've done is that we've recognised bedrock in the drill log. Okay, so we think we're somewhere down here. We're down at this interval, slightly weathered rock. It's the area where a driller would recognise the chips coming up as being associated with bedrock material as opposed to just sand or clay. Okay, so when we colour code those dots, we've still got quite a lot of data, over 100,000 points, and you begin to see some patterns. You know, the Murray Basin is pulling out here. You've got shallow cover in the upland areas. Tasmania is shallow. Unfortunately, a lot of the data didn't go much deeper than 200 metres. Most of it was quite shallow. So this is going to be a minimum depth map, okay? Because we don't have the drill hole information to really capture the deeper parts of the cover. Before I show you the result, just a few stats. So we ran this 100 model bootstrap aggregation analysis. We did it on a 90 metre resolution grid. So it's over 2 billion raster cells using 22 covariates. And it took initially, this is on a 24 CPU cluster, so a high NPC, about 7 days to run. Unfortunately, the out of sample correlation is quite low. It's 0.38. If we didn't do the filtering, it would be 0.23, so we've improved it slightly, with quite high uncertainties. And the mean regolith depth predicted was close to 30 metres. We've done some work within GA. Thanks for some IT support. We've got now a GA Windows server, 48 CPU, solid state storage, and we can reduce this time, particularly if we optimise the code, down to about 36 hours. But we also have a project at the NCI, and a lot of this code will be run there because we're going to get bigger as time goes on. So this is the output. This is the prediction using QBIS and those 22 covariates. So we're going from shallow 0 to 200 metres. Okay. And there are some useful patterns coming out of this, but we've got to remember that the errors are quite high, the model performance is quite low, and we can see that in the uncertainties. These red areas are high uncertainties and these areas are thicker cover. So you've got to be mindful of the reliability of the data. So let's have a bit of a closer look. So these green areas, the Murray Basin, all these more recent Cenozoic basins are coming out deeper, and you can see this when you compare it to the Paleogeographic Atlas. These yellow areas here are areas of sedimentation in the Miocene, mid-Miocene, Pliocene through here. The brown areas are areas of outcrop. There's no sedimentation. So these yellow areas broadly correlate to the green, and we've got these basin sediments through here. So in general sense, it's consistent with our understanding of the thickness of semi-consolidated, more recent sediments. Let's have a look a bit more closely. So we zoom in to an area. We can see that there's some variability up in the uplands, and that's quite consistent with regolith mapping that's been done up here. This is an old land surface which is slightly more deeply weathered, and of course we get thickening into the Murray and Darling Basin sediments out through here. So broadly, it's not looking too bad. I'm just showing you the good bits. Let's have a look at the Burdekin River Delta. So Townsville just up here. Okay, these colours again around. I've rescaled the data. So the greens are around 42 metres, and it shallows up here to almost no cover at all. And we can look at some other work that's been done there. This is a cross section using drill holes. You probably can't read it from the back, but from there to there is about 40 metres, so it's in the ballpark. In other areas, it underestimates the depth. So it's the first part. It's the first cut at doing this, and I think we've learned a lot from this exercise. We can do a better model in the future. So if you take more time now and go through those logs, drill logs, more systematically, and integrate other point estimates from magnetic and seismic data, you can get better correlations, and this is the work that's in progress with the Murray Basin. So the correlations are better if you can spend more time cleaning data. So this is an example here of so where we've got to with the Cenozoic and the Murray. These coloured dots here represent the drill holes that we use, and they're coloured according to where the basement depth is. Okay, and around the edge here we've got, I'm just showing you graphically, the key covariate data sets which underpin this model. So it's not, again, it's not interpolation between these points, it's correlations between all these data sets in the prediction. And when we look at the final model and the out-of-sample cross-validation, we're getting much stronger R-squareds with this sort of data. And that's a scatter plot of the model versus the observed. When we provide this data to our clients, the mining industry there's a lot more work we need to do on this. We'll give them our estimate of the depth through here, but we'll also provide them with their uncertainties. And there's these upper and lower confidence bounds. So this is the 90th percent uncertainty confidence value in here. Okay, I think that's important. So in this example, it's quite wide in the middle part of the basin, and that narrows as you get more topographic control in your predictions through here. The other thing we're going to look at is that, you know, to actually work with these huge data volumes, if we're using the covariates to come up with the predictions, why not use the covariates to select your site data and save a lot of time? Take out the redundancy in your site information. So, you know, can we select drill holes that represent variations of environmental covariates in feature space? Okay, that's what we want to do. So one way of tackling this is that we choose or put together, compile our key covariates and run a k-means clustering algorithm over it. And so we're looking at sort of feature space. And then within that we select drill holes which are close to the centroids of those clusters. So we're selecting targeting drill hole information which is representative of the covariates that we're going to use to model or predict from those points. We might save a lot of time, so that's something we're looking at. So I'd just like to end with a couple of conclusions. One is that it's a very different approach to standard sort of mapping. Data mining and knowledge discovery, which is part of this, provides a powerful approach for predictive quantitative mapping of the cover, and it importantly gives you uncertainties of those predictions, which I think we need to do because it is difficult and there will be high uncertainties in places. It allows explicit prediction of individual properties of cover materials at the scale of your covariates, so it's very important. One of the issues that we might find is that a lot of our covariate data sets, if you think about satellite images and so on, they're really mapping surface features. As we go deeper, we have much less of a richness of covariates, and so we've got a skewed surface or near surface covariate suite, and there might be issues as we go deeper, and that's something that we'll discover as we continue developing these methodologies. And also finally, the quantitative modelling requires quantitative measurements for calibration and training the data. I use an example of surface geochemical survey data. It's very precise information and it's consistent for that area. But if we're looking at national models and we're trying to run national models of surface geochemistry or predictions, we need to consider the consistency of those geochemical surveys and the coverage. Do they represent the variations that we see in the covariate space? So they might be potential limitations for future upscaling of these methodologies. Thank you very much.